Good morning. I'd like to move on to now the second part of our recitation for today, where we go over some basic calculations having to do with Phasors impedance and doing circuit analysis with phasors. I'd like to start out first by addressing some problems about how we would convert real time varying voltage values into phasors. So in this case, we're only considering voltage or current inputs where the value of, or the function of the current or voltage is sinusoidal. So to give an example, let's start out with a current I1 of t, which has been defined as a real function of a sinusoidal real function as follows: 10 sine of 8t plus 75 degrees. Now, how would we convert this into its phasor value? So the first thing that I'd like to remind you of is just the derivation that we had of the phasors initially, where we actually applied Euler's formula to the sinusoid. And what we did was, first we converted the sine into a cosine. So step one, if you have a sine, convert this to a cosine. How do we do that? From trigonometry, I'd like to remind you that sine of any angle theta is equal to the cosine of 90 degrees minus theta. So we can write this time varying function simply as 10 times the cosine of 90 degrees minus 8t minus 75 degrees. And then also remembering that the cosine of a negative angle is the same as the cosine of the positive angle, we can kind of flip the signs on the arguments here, and we can write this as 10 times the cosine of 8t minus 15 degrees. Now, if we apply Euler's rule on this, remember that the cosine is the real component of a generalized complex variable. So we would write this as the real component of 10 times e to the j 8t minus 15 degrees. And now what I'm going to do is I'm going to separate out the frequency dependent component. So the frequency dependent component would be the 8t term, because that depends on time. And I would write this as the real part of 10 times e to the minus j 15 degrees times e to the j 8t. So in this case, 8 is our value of omega, which is the frequency in radians. And our actual phasor is this coefficient here. So this is our phasor. And just to remind you, we represent phasors as capitalized variables. So capital I1 is the phasor for the real function I1 of t, and then that would just be, right now, 10 times e to the minus j 15 degrees. Please make sure you're careful about expressing the units of the phase. So if it's a degree value, please make sure you mark the degrees, because the default assumption is that phases are in radians. And I just want to drop a note here so that you remember this. So if you would just write 15, then I would by default assume that that's radians. So just make sure that you're very clear and label your angles with the degree symbol if you are using degrees. Okay, let's move on to another example. Let's now consider the function I2 of t, which is equal to minus 17 cosine of 9t minus 25 degrees. So based on what we did in the previous problem, observe the fact that actually to write the phasor, we don't need to go through and kind of rederive using Euler's formula each time. All we have to do is recognize what the amplitude and the phase terms are in the function and make sure that we've written this in terms of cosine. And then we can just write what the result is. So I2 is going to be minus 17 times e to the minus j 25 degrees. So all we did was pick out what the amplitude and phase term was and combine them. If we want, we can combine the negative sign into the phase term by remembering that minus 1 is equal to e to the j 180 degrees, or if you like, e to the minus j 180 degrees. It's fine to consider either way. If we use the relation that it's e to the j 180 degrees, then we can also write I2 as simply a positive 17 times e to the j, and now we have to take 180 degrees minus 25 degrees and I believe this will give us 17e to the j 155 degrees. Okay, so both of these two forms here are acceptable ways of writing the phasor for I2. Let's now consider how we might combine phasors that are being added together. So let's now see how we can write what the phasor would be for the summation of two functions. So let's take 8 cosine of 6t minus 45 degrees, and let's subtract from that 4 times the sine of 6t. Now, the first thing that you have to realize is that there is a phasor for each frequency, and we can only add phasors of like frequencies. So only phasors of the same frequency can be summed. This comes from the fact that the phasor is actually a scalar multiplicand to whatever the frequency term is. And so if you think about the original form that we derived here, where is it? Here. So we can sum terms that are like a e to the j omega t plus b e to the j omega t, and we can write this as a plus b e to the j omega t, which means that we can sum the phasors of the same frequency. But if these omegas were different, we wouldn't be able to proceed beyond that. So the main reason for why this rule that I've written here is true, again, just derives from the mathematics of complex numbers. So let's check in this problem. We've been asked to do a summation or a subtraction. Are the frequencies the same? Well, let's look at the function. To understand whether the frequencies are the same or not, we need to look at the coefficient of the t parameter. So the coefficient of t is 6 in both of these functions, which means that yes, in this particular problem, we can add the two phasors together. So let's write I3 as the sum of two phasors. This is going to be 8 times e to the minus j 45 degrees. Again, we just peel out the amplitude and the phase terms from here and then combine it into the complex exponential for the scaling factor. And then now we have a sine term here. And remember that the sine is equal to 90 degrees minus the cosine. So this is actually cosine of 90 degrees minus 6t, which is equal to the cosine of 6t minus 90 degrees. So the phasor for the second term then would be minus 4 times e to the minus j 90 degrees. And now we have to add these two complex numbers together. So to do this, we have to use Euler's formula and convert these into rectangular format because it's easier to sum complex numbers which are in rectangular format. So this is now going to be 8 times the cosine of minus 45 degrees plus j times 8 times the sine of minus 45 degrees minus 4 times the cosine of minus 90 degrees minus 4 times j times the sine of minus 90 degrees. Now, the sine of and cosine of 90 degree simplify. So the cosine of minus 90 degrees is the same as the cosine of plus 90 degrees, which is equal to 0, actually. So this is equal to 0. And the sine of minus 90 degrees, is equal to just minus 1. So let's write that in this fraction here. So if we were to go and this time continue the calculation onto the next page, we could write I3, and just so we can see what we did before in the previous slide, maybe I can kind of slightly enlarge what we had previously so you can see that on the left. But I3 now is going to be 8 times the cosine of minus 45 degrees, which is the cosine of positive 45 degrees. And if you think of the 1, 1 square root of 2 triangle, the cosine of 45 degrees is 1 over the square root of 2. So this is 8 times 1 over the square root of 2, plus j times the sine of minus 45 degrees, which is minus 1 over the square root of 2, minus 0, and then we have plus J4, which comes together here. So once we have this, now we need to group the imaginary and the real terms together. So we have 8 divided by root 2 plus J times 4 minus 1 over the square root of 2. And this is now going to be the expression of our phasor in terms of rectangular coordinates. What happens now if we'd like to express the combination of these back in terms of its real-time functionality? So what I want to do is I want to go from I3 back to I3 of t. How would I go about doing that? To do this, I first need to express this phasor in terms of polar format. So let's calculate what the magnitude and phase of this would be and write the phasor in polar format. The real component is 8 divided by the square root of 2. So I would have 8 divided by the square root of 2 squared plus the square of the imaginary component. So 4 minus 1 over the square root of 2 squared. And then this would be e to the j tangent inverse of the imaginary component, which is 4 minus 1 over the square root of 2, divided by the real component, which is 8 over square root of 2. Now, I don't want to spend the time now to kind of go through and calculate this out, but you could whip out your calculator at this point, and you could write then I3 in terms of just capital amplitude A, e to the j theta, okay, where A is defined as the square root term we have here, and theta is defined as the tangent inverse of this huge argument that we have here. Again, you know, A and theta we find from the calculator at this point. But we ultimately know what A and theta are. If we then want to go back to the form of I3 of t, the way we would do that is we would write the magnitude of the phasor. So this value A is just going to be A over here. We have cosine of the frequency. So whatever was the frequency in the original problem, which in this case was, we had a frequency of 6, we would write 6t and then plus whatever theta was. And this would be what our resulting current value was in amps, given that we added those two input currents, as we did in the previous problem, or in the previous slide, not the previous problem. So let's do another example of how we would do this. So let's now take as an example, let's say a current I1, which is equal to 6. So this is the phasor, 6e to the j 60 degrees at a certain frequency. So remember, the phasor is only understandable if you define it for a certain frequency. So let's say I've defined this at a frequency of 60 hertz. Since this is in hertz, I first need to convert this frequency into radians. In radians, the frequency is 2 pi times 60 radians. So when I'm now converting this back as an I1 of t term, I would write this as 6 times cosine of the frequency, which would be 2 pi times 60 times t, plus the phase. The phase here is just going to be the argument of j, which is 60 degrees. So I'd write plus 60 degrees, and this is amps. So this is how we would write the real valued function that corresponds to the phasor I1 equals to 6 e to the j 60 degrees at a frequency of 60 hertz. What would happen if f was something else? Let's say f was now 1 megahertz. How would that change the way we write the phasor? Well, then we would write, let's call this I2. We would write I2 of t as being 6 cosine of 2 pi times 10 to the 6t plus 60 degrees. And this is amps. So you can see why I say now that you really have to have the frequency matched with the phasor, because the phasor doesn't tell us the frequency. It only tells us what the magnitude and phase is of this cosine. Okay, let's do another example right now. Suppose I now told you that I had a phasor I2, which was equal to minus 4 angle of minus 120 degrees at a frequency of 3 megahertz. How would I write this? Well, first remember that this angle notation is equivalent to writing this as -4 times e to the minus j of 120 degrees. And then you can convert back to the time domain by just taking this as -4 times the cosine of the frequency. And remember to convert to radians. So it's 2 pi times 3 times 10 to the 6 times t. And then plus the phase, which in this case is minus 120 degrees. And of course, this has units of amps, if we take that into account. Okay, so this kind of summarizes how we would do some of the basic arithmetic on phasors, which is the way we're going to represent the voltages and currents in circuits. Let's now take a look at the issue of impedances. So you might remember from the previous lecture that the impedance of a resistor is just the value of the resistance. The impedance of the inductor was J times the frequency times the value of the inductor. And the value of the impedance for a capacitor was 1 over J times omega times C. So how do we actually calculate things if we're given real values? Suppose we have a resistor value of 1K. Well, then the impedance would just be 1K. There's no change there. But suppose we were told that we had an inductor value of 30 microhenries. We have to be told the frequency value. In the case of the resistor, the impedance of the resistor doesn't change with frequency. But the impedance values for the inductor and the capacitor do change with frequency. So I have to tell you what the frequency is. Let's say this is at 1 megahertz. How would we calculate the impedance? Well, we would substitute these values. We would say J times the value of the frequency, which would be 10. You have to convert it to radians first. 2 pi times 10 to the 6 times the value of the inductance, which is 30 times 10 to the minus 6. And then you could calculate what that turned into by just multiplying out. I think in this case, it just becomes J times 60 pi. The 10 to the 6 cancel with each other. What about for the capacitor? Let's suppose that the capacitor value is 50 microfarad. And again, let's say that we're looking at a 1 megahertz value for the frequency. Then we would write that the impedance of the capacitor is equal to 1 over J times 2 pi times 10 to the 6, this is the frequency, times 50 times 10 to the minus 6 farad for the capacitance. And if you calculated this out, then you get 1 over J times, this is going to be 2 times 50 is 100, so you would get 100 pi. And then, you could divide through if you really wanted to, but this would be your impedance for the capacitor numerically in terms of farads, what you would use. So now let's combine all of these ideas and just do an analysis of a basic circuit. And let me show you how you would convert the problem from the time domain into the frequency domain. So suppose the problem asked you to calculate the source current. So I have a source voltage, Vs of t, and I want to calculate what the source current would be given that I'm connected to a resistor of value R, a capacitor of value C, and an inductor of value L. And I'm actually going to write on the right-hand side here what the values are. R is going to be 1 k ohm, L is going to be 120 millihenries, and C is going to be 5. Okay, I think we're back recording again. Let's share the screen. And let me make sure that we're still recording. Okay, I'm not sure at what point the internet cut out, so let me just summarize the problem. We have a circuit that has a resistor, a capacitor, and an inductor in it, and we're driving it with a sinusoidal source voltage, Vs of t, and I want to calculate what the source current, Is of t, would be, and I'm telling you that the sinusoidal input voltage is 15 times cosine of 5 times 10 to the 4 t minus 30 volts. And I've been given R, L, and C values as I defined above. So the first thing that I need to do is I need to convert everything from the time domain into the frequency or phasor domain, if you will. So this means converting Vs of t into the phasor Vs. Let's start there. It's going to be 15 times the phase value minus 30 degrees. So this is e to the minus j 30 degrees. So there's my phasor. And now how about our elements? Well, the impedance of the resistance is still just 1 k ohm. The impedance of the inductor is going to be j times omega times L. The frequency we have to glean from the way we're driving it. In this case, we're driving it with a frequency of 5 times 10 to the 4. So we should substitute over here 5 times 10 to the 4. And then we multiply by the value of the inductance, which is 120 millihenries. And we have to multiply all this together. So let's kind of do out the math. I think 5 times 12 is 60. So this would be 600 times 10, because 10 to the 4 times 10 to the minus 3 is 10. And we would get J times 6,000. And if we use the units of ohms for impedance values. Now let's go through and calculate what the impedance of the capacitor would be. So our ZC is going to be 1 over J omega C. So 1 over J times the frequency, which again was 5 times 10 to the 4, times the value of the capacitance, which was 5 times 10 to the minus 9. Let's go through the math now. We get 1 over J times 25 times 10 to the minus 5, which is going to be 10 to the 5 divided by J 25. And I can split this into 100 times 1,000. And if you divide through, you can find that this turns into 4,000 divided by J. It's common to not leave J terms in the denominator. So we would more commonly write this as minus J times 4,000. And remember, just like, how do we convert that? If you would multiply J by 1, where we've represented 1 as J divided by J, then you would get J divided by J squared, which is minus 1. And then this gives you minus J. So a J in the denominator comes up as negative J. But this is the value of impedance that we would use in the circuit. And then now we would express the actual circuit itself in the phasor domain as follows. We would still have our voltage source, but now it's going to be driven with a phasor Vs. My resistor is now going to have an impedance ZR. My capacitor will have an impedance ZC. My inductor will have an impedance ZL. These are the values that we've calculated before. And I'm going to find the phasor IS. Once we've converted to the phasor domain, and we've replaced everything with impedances, the way we combine the impedances and do the analysis is exactly the way we would do the analysis with a resistive circuit. Because remember, once you've converted to impedances, the generalized Ohm law kicks in, which means that in general, the voltage is equal to the impedance times the current. And what would normally be a second order differential equation if we had tried to solve this circuit in the time domain now just turns into an algebraic problem, but we're doing complex algebra as opposed to solving differential equations. So we could calculate IS by just taking the total voltage and then dividing it by the equivalent impedance it sees. The equivalent impedance it sees would be the parallel combination of ZC and ZL in series with ZR. So you can see, without solving any differential equations, with just one line now, I've been able to write what the phasor is for my answer. Of course, the devil is in the details. We have to work through the complex arithmetic now to reduce this algebraic expression into a single complex number of polar form. So let's now see how we would work through and do that. Let's start by first calculating the parallel combination of ZC with ZL. So again, the impedances behave just like resistors. So ZC parallel with ZL would just be ZC times ZL divided by ZC plus ZL. And now we actually have to replace for the values that we found earlier. So this is going to be J times 6 times 10 to the 3 times minus J times 4,000 divided by the sum, so it would be minus, minus 4 minus 4,000 plus 6,000. So now let's calculate this out. Minus j times j is equal to just 1. So the numerator is going to be equal to 24 times 10 to the 6. The denominator is going to be plus 2,000j. And if we divide the 2,000 into the numerator, you'll get 12 times 10 to the 3 divided by j, which remember is just minus j times 12 times 10 to the 3. So this is the parallel combination. And now we can substitute into the overall expression. So first we substitute the value of our voltage phasor, which we found was 15 e to the minus j 30 degrees. And we're dividing that by the sum of the resistance, which was 10 to the 3, plus this parallel combination, which we've now found to be minus j12 times 10 to the 3. So now we have to work through this expression. One thing that we can do is just kind of factor out the 10 to the 3 and say that we're now going to be in milliamps from now on. And I can write this as 15 e to the minus j 30 degrees of 1 minus j12. And now the next step is I have to actually go through and convert this denominator into a polar format. So I'm going to say that IS is equal to 15 e to the minus j 30 divided by, it's going to be the square root of 1 plus 12 squared, which in this case, actually, it's going to be approximately 12 because 1 is so small. It's going to be approximately 12. And the angle is going to be equal to e to the minus j tangent inverse of 12. And now we can combine all of these terms. So this is going to be 15 divided by the square root of 145. I'm going to keep it in exact terms so that you can follow it along. And then this is going to be e to the j. Now this negative tangent inverse 12 term is going to come up as a positive term. So this is going to be minus j tangent inverse of 12 minus the tangent inverse, I'm sorry, not the tangent inverse, it's just 30 degrees, minus 30 degrees here. And again, you can calculate what these values turn out to be in the calculator. For now, let's just write this as a generic a e to the j theta, where this coefficient here is equal to a, and this term here is equal to theta. How would we now convert this back into the time domain? Well, we would write is of t as having the magnitude of a times the cosine of whatever the frequency was. I believe in this problem, the frequency, if we go to the beginning, it was 5 times 10 to the 4. So this will be 5 times 10 to the 4 t plus whatever phase value we find. And this is going to be in terms of amps. Okay, so this just gives an example of how we can step through and use complex analysis to solve a circuit really which, you know, second order analysis, I have some examples of it under my notebook so that if you're interested in learning the time domain analysis of second order circuits, you can go ahead and take a look at it. But it's believe me, it's much more involved than what we've just done here with complex analysis. So I'll see you on Wednesday for our next recitation. If you have any questions about these lectures, please let me know. It would be good if you can listen to these recitations before lecture and come equipped with your questions so we can go over them interactively. This is all for me for now. I wish you all a good night. Take care. See you later.